So arc length is something also not entirely new, because if you have taken Calc 2, at the beginning there was a application about integrations. Okay? So back then it was two-dimensional figure, but then you probably have seen this kind of formula already. So here, today we want to motivate this arc length formula, which is, let's say, here we have something slightly different. But if you remember, the way that we derive this arc length formula in 2D is that we Riemann sum. So here the idea is that you are traveling along this space curve now, and then let's say for the parameter t equals a, it will be at the starting point right here. And let's say the endpoint is right here where t equals b, right? And what you want is you want to calculate the distance that you travel if you are just traveling along the space curve. Starting from time point A to time point B is the length. Okay, I'm still gonna use red, but I'll make it kind of low. So let me try doing that. So you're traveling along the space curve. You want to get the length, right? So the formula here is going to be the integral, definitely integral from a to b of the square root. So this is something that you may see from here. It's f prime of t squared plus g prime of t squared plus h prime of t squared, okay, under the square root that you're integrating. And you realize that if your vector function is fgh, right, then this is exactly integrating the magnitude of your tangent direction, okay, the tangent vector. For curve Rt, which has components f of t, g of t, h of t, from time point t equals a to time point t equals b. Okay. So now, today let's quickly motivate this this equation, okay, by just doing the Riemann sum method. Question: how do we derive this formula? So basically, what we do is that this is this red solid curve is definitely curvy. So it's not really easy to do it. But then what we do is we divide up this interval from a to b into, let's say, n equal pieces, right? And then every piece we're gonna do a line segment, and we can calculate the length of a line segment, right? So basically, we know in the three-dimensional space, if you are given 2 points and you just draw the line, straight line between those, right? And you know that if the coordinates are x0, y0, z0, and x1, y1, z1, then you know the distance between these three quarters, right? Distance equals the square root of x1 minus x0 squared plus y1 minus y0 squared plus z1 minus z0 squared. Okay. I'll make it longer. That's something we have the knowledge of. Okay. And now let's just systematically break the original curve up into pieces. Okay, so now let's say this is the space curve that we want to calculate the arc length. And let's say this is t equals a, the starting point, and let's say this is t equals b, the endpoint. Okay. And now, so when we break it up into pieces and we just draw line segments just along the path, and then what do we get? Essentially, so we always think t equals a as t0, and we think the last time point is tn. Right? So that's t0, that's tn. And basically t1 is possibly here, t2 is possibly here, t3 is possibly here. Basically, if we break it out into equal pieces, right? And then that delta t is going to be b minus a over n, right? So n pieces. And then basically we just separate it by the time intervals, and then we just collect as maximums, right? And the thing is, although here it doesn't look really accurate in this illustrated figure, but then the more pieces, the larger n that you use, the better approximation it will be, right? And then we push n to infinity, and we just sum up all these line segments. So for each one, if you take a closer look, so let's just look at this one, let's say. Just zoom in, okay, close up. So what you have is a curve, but then you just connect it by two endpoints as a line segment. So here, let's say we have t equals to, now we have t0, t1 all the way up to tn, right? So let's call this t equals to ti. Okay, so this is the ith input point. Ith. And then this is t equals to, now instead of ti plus 1, we just say ti plus delta t. Okay. So this is just a tiny increment of the input. Okay. And then we can know that the solid point on the left is what is f of ti, g of ti, h of ti, just the coordinates. And of course, this point is what? This point is f of ti plus delta t, g of ti plus delta t, and finally h of ti plus delta t. Right, now we know the positions of the 2 points, and then we just do what? We just do the line segment, right? So length of line segment. So it's going to be a large radical. And now we just do the changing the coordinates. Okay, so f of ti plus t minus fti squared plus g of ti plus delta t. The latter g coordinate minus the prior within this bracket of the square, and then we have h of the latter minus h of the prior. So this is the exact length of the line segment. But now notice that for each difference, if you think about this actually can be represented by approximately by the derivative times the changing input, right? So that's something we have learned from Calc 1. Okay, so this is f prime. So if you think about the definition, f prime of ti, so the derivative at the starting point, this is the limit where you just push the change of input to 0. So the slope of the tangent equals to the approximation using the slope of the sequence. Okay, so So f of ti plus delta t minus f of ti over delta t. This tells you now the numerator right here is approximately the slope tangent times the changing input delta t. Okay. So f of t. So this is what's it called? The linear approximation. Okay. So the change in input is approximately the slope tangent times delta t. And here delta t is always positive, okay, if you recall. Delta t is just b minus a over n, which is positive. And then we can rewrite the thing above. Now, it's going to be simpler. So at every coordinate, we just replace by, now you see, for f, it's f prime, the derivative at the left-hand point, times delta t whole thing squared, okay? Plus, now g is going to be the same. So we do g prime, we approximate by g prime, pi times delta t again, because the change in input is always the same, right? And then for h, the difference in h, we're going to do the derivative times the change in input again. And now this is nice. So f prime squared, g prime squared, h prime squared, that's matching up with the equation that we want. And at the same time, you see delta t squared is everywhere, and then they can be factored, and then they can be dragged out of the radical. Yeah. So this thing now becomes delta t, which is what's in common, and you just take it out of the square root. And you know it's positive. And then what you have remain is f prime squared, g prime squared, and h prime squared added up, right? And now you see, okay, this expression pretty much is what we want. So delta t will, in Riemann sum, will become dt. So f prime ti, g prime ti, h prime ti, they will eventually become just f prime of t, g prime of t, h prime of t. Okay. The functional values at the sample point, but the sample point here is just ti. It's just the starting point of the i's interval. Right. So adding the above approximation with t equals to t0, t1, all the way up to tn, and taking limit of sum as n goes to infinity, we will have the following chain of inequalities. So L representing the arc length, we know the more pieces, the better, right? So when n approaches infinity, we want to get the limit. The limit of what? The limit of the sum of all the line segments. Okay. So I goes from 0 to n, well, n minus 1. Well, because our endpoint is Tn, right? So there are n pieces. And then we're just summing up these, right? But here I want to put the delta t at n, so it's going to be f prime of ti squared plus. So of course, if you are doing an iPad, using an iPad, you can just copy the previous line here. Let's write one more time to emphasize that what we are summing. So we are just summing up every piece, n pieces of line segments, and then we push the number of line segments to infinity, okay? And if your function is well defined, and then what you are summing up, this part, the functional part is continuous, and then by definition, this is the Riemann sum of the following. It's definitely integral, right? So it's the integral from a to b of f prime of t squared plus g prime of t squared plus h prime of t squared ct, right? Ct at the end. So you see all the TIs, they are sample points of the inputs at every subinterval, and then delta t just represents the tiny little length of the time interval, which is now dt. Okay, so ti will be replaced by t, and then delta t will be replaced by dt. Pretty standard. But now, if you want to rewrite this formula, this is an integral from a to b of the square roots. Now, f prime is actually what? F prime is actually dx dt. G prime is actually dy dt. Okay? The rate of change of the y coordinate. And finally, dz dt is h prime. Here, since x is f of t, y is g of t, d is h of t. On the space curve. Right? And of course, we can write it another way that we have done before. So we know this is what this is the magnitude, right? This is the magnitude of the tangent direction. Okay, so just we're just accumulating r prime of t. Since the curve is described by t. Okay. So as long as you denote the space curve to have a name a little r, then r prime just the magnitude of r prime just represents this expression. Okay. And we're gonna use a large box to enclose this chain. Pretty standard, right? Now, example. So just think about that space curve, which has coordinates cosine of t, sine of t, t. So this is something we have seen. This is the helix that we actually have a figure. So let's it's 14.1. Let me copy the figure from before. Right here. Right. So basically, now in this example, we want to calculate the arc length for this space curve. So what do we need? If you think about it, we just need to integrate this part. Okay? So we calculate r prime, the tangent direction, the tangent vector, and then we take the magnitude, and then we integrate. Okay? That's the process. So let's calculate r prime first. So if you recall, the tangent direction, we just do component-wise derivative, right? So cosine gives you, so the derivative of cosine is negative sine. The derivative of sine is cosine. The derivative of t, so t is power function t to the 1. The derivative of that is 1 times 2 to the 0, so that's just 1 power to the 1. And then we're almost there. So here I want to also specify the time interval, so. Otherwise, this curve will not really stop, right? So here, t goes from 0 to, let's say, 2 pi, right? Then we just want to calculate the arc length along the curve for one period, right? Starting from the bottom solid red point to the top solid one, right? From 0 to 2 pi. One period. So compute the arc length from point 100, where t is 0, to 102 pi, where t is 2 pi here, on the above curve. Then we just utilize the equation. And so we know what our prime is already in red. Right? So cap L is going to be the definite interval. So we know that t starts from 0 to 2 pi, so that's our endpoints of the definite interval. And then we integrate our prime dt, taking the magnitude dt. So now we're here to just substitute, right? So the magnitude, we are taking the vector negative sine of t. So firstly, we just directly substitute, and then we take the magnitude. So negative sine cosine 1. And then we put the things on the radical. And so one thing I can assure you guys is that when we are calculating the arc length, the functions are definitely the vector functions are definitely going to be nice enough so that the radical is not difficult to calculate. Well, I think in Calc 2, you probably have seen some more complicated curve in 2D that you want to compute squares right here and then check out them. But here it's not going to be that complicated. So we just take the component squared and sum up, right? So we will have negative sine squared plus cosine squared plus 1 squared. And you see, okay, we have negative sine squared, that's just sine squared. Cosine squared, they have the same argument, so they add up to be 1. Right? So essentially, you're just accumulating square root 2. So here, okay, this is a constant, the antiderivative. So basically, if you want to write down the antiderivative, this is square root 2 times t. And then you evaluate at the endpoint t equal to 0 and t equal to 2 pi. So it's just going to be square root 2 times 2 pi minus square root 2 times 0. So it's just going to be square root 2 pi square root 2. So you can say here, of course, it's kind of obvious that this is true, right? You're integrating a constant over the interval from 0 to 2 pi. But here, we're writing these 2 additional steps because if you observe, as long as you can write down the antiderivative expression for the integral, then t equals to 2 pi, the endpoint of your interval, it can actually be any constant, right? If you just replace it by a variable, let's say b, a parameter b. Okay. And then, as long as you can write down the antiderivative of the magnitude of our prime that you already have, then this becomes a function in terms of your endpoint of the space segment. Okay. So any questions so far about this example? Yes.
How did you go from sine squared to cosine down to like square root of 2?
Oh, so here, let me question. So just be reminded that sine squared of t plus cosine squared of t equals 1 everywhere. Okay, so this is a very important identity for this kind of question because like I said, we don't really have we wouldn't really give you very complicated radical for you to handle, but this is definitely important. The Pythagorean theorem, right? Sine squared plus cosine squared equals 1 if they have the same argument. Right here. Any other questions? Okay, so now that remark we were just talking about. So if you change the endpoint of the interval for any parameter b, and then you will get a function in terms of b, right? So that's just describing the arc length that's along the curve that's starting from t equal to 0 to t equals some b. Okay? And that will be a function in terms of b. So to illustrate in a figure, x, y, z, space curve. So originally we have what we have t equals a right here. Originally we have t equal to b right here. Okay? But then now let's say for whatever time point t, we can use that t as the endpoint as a parameter set, and then we can calculate the arc length for whatever endpoint. Okay? So it doesn't have to be t equal to b. Right? It could be something in between. So we can define what we call an arc length function, little s of t, which equals the integral from a to t accumulating our r prime. So now here we're using t already, so we're going to use another variable. We're going to use another letter in the integral. Okay? So it's now r prime of u du. So you notice that here the upper limit of the integral is now some variable t. Right? So now basically this just says, okay, if my t is right here, then I'm just calculating the arc length along the entire space curve segment, right? But if my t is somewhere in between, say right here, I'm just calculating the arc length for this piece, right? That's exactly what we are doing right here. Okay? And if you want to put the things explicitly, this is the Lagrange integral from a to t, of course. So now here we're doing u in the for the variable that we're integrating. So it's going to be dx du squared plus dy du squared plus dz du squared. So this s of t, this little s of t is called the arc length function. So basically calculating starting from the time point A to time point T, the arc length that you have traveled along the space curve. Okay? And of course, you know from the fundamental theorem of calculus, So if you do the derivative for both sides. On the left hand side, you will get S prime. And on the right hand side, you will get what? So you're integrating R prime of U, right? So you just so now if you do the derivative, you will get R prime, take the magnitude, and then you evaluate at the time point t. Right? So it's just going to be R prime of t taking the magnitude. Okay. Example. So if you think about that helix we just did, so when we have Rp equals to cosine p, sine p, t, where t goes from 0 to 2 pi that we have done just now, this arc length function, little s, is going to be the integral from 0 to t, right? So we just replace that 2 pi. That's t right here. So we actually know what R prime of u is. R prime of u is negative sine of u, cosine of u 1, right? And then we have done this calculation already. So this is from 0 to t, the integral of square root 2 du. Okay? So this is indeed a linear function in terms of t. So square root 2t. And now if you think about it, basically S of t is definitely going to be a function that relies on this upper limit of the integral. Okay, so when t gets larger, this S of t gets larger, and at the same time, if you think about this, basically if you are just aiming at the arc length, you're just saying, okay, I walk along the space curve. I want to know what the time point that is if I travel 10 feet. Okay. So given the arc length that you have traveled, you want to know the time. That's also that also can be done from this relationship, right? You see, this is a kind of a function of relationship. Okay, so S relies on T, and at the same time, T relies on S. Remark. If so, this is a functional expression, the functional relationship, and also you can think about it as a parameterization. Okay? So originally you have a parameter t, but now you can just use another parameter s to represent the whole thing. So if we set parameter to be little s, which is expressed by s of t, which is square root 2 of t, then this relationship tells you, okay, if you give me t, I can calculate x, right? So the reverse, okay, the inverse function is what? Is t equal to, we just divide both sides by square root 2 if you want to solve for t, right? So that's just little s over square root 2. So this is actually the inverse function. And hence, we can eliminate the variable t in the curve. And we do that by doing the substitution right here. So R is defined by t, right? But now we just replace t in terms of s. So it's going to be t of s. We just substitute t of s, the functional expression, here into the curve. And what do we get? We will get what? So t is now whatever you see t, you just replace by s over square root 2. Okay? It's going to be cosine of s over square root 2. I can use a bracket to enclose this inner functional calculation. And it's going to be sine, t is now replaced by s over square root 2 again. And finally, the last entry about the time is now s over square root 2. Okay. So this is another parameterization. Okay, so now the space curve is parameterized by our arc length, right? And here it's exactly the same curve. It's just we're just using a different parameter. Where S is now from 0 to 2 square root 2 pi, right? So at the end, the arc length is at most 2 times square root 2 pi. This is the arc length we have computed, right? And now, just recall that originally t used to be from 0 to 2 pi, right? And here, how do we get this interval? You can think about this as from 0 to the maximum arc length, of course. But at the same time, if you just want to start from scratch, you know t is what? T is s over square root 2 from here, okay? And then what you can do is you multiply every side by square root 2. That will give you the interval of s. Right? So that's another way to think about this. So the above is a parameterization with respect to arc lengths. So as you think about it, if you parameterize your time in different ways, then along the same space curve, you may have different parameterizations. Okay? So basically, if you think about it, you can imagine that the space curve is like a road in the space, and you are just traveling, you're like driving along that a space curve. But then, if you drive slow, then it will be so the arc length will grow slowly, right? But then when you're changing the direction, this is going to be really gradual. And then if you travel really fast, the arc length will accumulate much faster. And then if you are just turning, then it will be much sharper turns. So that's something relying on the parameterization that you use. Okay, so here when we talk about the parameterization with respect to the arc length, then this will only rely on the arc length itself. Okay, so it doesn't really depend on the speed that you travel. Okay, so this is something that motivates the next section called the curvature.